initiate, this is stop, this is stop. So from here, your ribosome particles will bind, initiate, then next triplet, next triplet. So the sequence will go. The first amino acid AUG codes for methionine. So that's why it is called initiator. Correct? First codon or initiator codon. It is the methionine, and often the protein, some of the cases, during translation, methionine is the first amino acid, but it has been removed later on for variety of function, protein function. Okay, so we will talk about, let's say there is another A or G in the middle, because in a protein there should be multiple methionine, correct? So one at the beginning, one at the middle, and several. So how does cell decide, correct, distinguish between start codon methionine and the middle, correct, methionine? We'll talk about that. There is a technique of that cell. But let's talk about a little bit about translation process. So whenever there is translation, your ribosome particles binds to the messenger RNA. In the ribosome site, there is three sites. One is called A site, another is called P site, this is called E site. A site is the acceptor site. P site is where it gets the peptidyl transferase. So your tRNA, right? So this is your mate, another amino acid comes here, right? Another amino acid comes here. So eventually you need to form the peptide bond, right? So you have CH CO2 minus HCN plus R, and you have to make the peptide bond between these two. So basically you make CH R CO NH. This is a chemical reaction you have to produce, right? Peptide bond formation. And this peptide bond will form between these two neighboring amino acids which are brought to the neighboring genetic code, and this reaction has to be catalyzed by the ribosome particle. So acceptor site in the ribosome brings a tRNA, and once it is translocated to P, this is exactly the peptide bond formation territory. So basically, these two amino acids are connected, and ribosome moves, and the protein is exited by exit channel. Okay. So A is the acceptor site, P is the peptidyl site, E is the exit site, and you can see. And now your additional tRNAs are aligned downstream. Does it make sense? So additional tRNA with amino acids are aligned, so here they are connected. You can see the peptide chain is growing and exiting. So basically, the peptides are synthesized by these tRNA molecules, and peptides are bonds are formed by the enzyme, and this time this enzyme is not a protein, rather RNA. Now we want to talk about a little bit initiation. The initiator tRNA, the point which I made, that if there is other methionine inside the protein, how does cell distinguish between the first methionine versus inside the methionine, correct? So the way it does that initiator tRNA methionine group is formulated so this is the initiator tRNA AUG complementary AUG. So you have the methionine, and this methionine, this part is connected to the acyl linkage with the adenine, correct? Adenosine. Does it make sense? And the amine group of this methionine, and if this methionine, this tRNA is the initiator tRNA involved in translation and initiation, first AUG. Does it make sense? Then this methionine amine group will be formulated. This is formyl group, aldehyde group. Does it make sense? So rest of the methionine tRNA, this amine is not formulated. So now you can distinguish if the N is formulated, it's the initiator tRNA. Does it make sense? So that's how it makes the distinction between initiator tRNA and inside the protein methionine. The initiator tRNA is formulated methionine, it's called F-met tRNA initiator met. Does it make sense? Formyl transferase, there is an enzyme which adds the formyl group to the amino group of the initiator methionine group. N-formyl methionine tRNA met is only used for initiation, and regular methionine tRNA is used for incorporation of methionine internal site. Does it make sense? No? It does not make sense?
Can you explain it again?
Okay. So you have a big protein, correct? The first amino acid has to be what? Methionine, correct? So, but in a big protein you have many more methionine groups. So how does cell decide which one is initiator, correct? So the way it does that, the methionine group, which is the first amino acid, which will start the translation, that methionine group is going to be modified here. So normal methionine, this NH will be free, but in this case it is formulated, aldehyde group modification. So now we have a methionine which is specific for translation initiation. Does it make sense now? So this is what we are telling that N-formyl methionine is only used for initiation, and regular methionine tRNA is used for internal methionine incorporation. This is formyl transferase which adds the methyl group. N-formyl methionine is the first amino acid in nuclear protein. N-terminal of methionine remove post-translational later on. Okay, so few things already we did. This is the N formulation reaction. tRNA connected to the methionine, and this amine group is connected to the aldehyde to distinguish it from the internal methionine group. There is a lot on initiation, but I think I will skip the regulation of initiation. But first, I want you to know the basic concept of translation. Correct? You have a mRNA, you have genetic code, you have start codon. Correct? And then ribosome comes and assemble ribosome has the acceptor site. At the peptidyl transferase site where the chemical reaction takes place, correct? The exit site. And the first codon is AUG, which is specific for methionine, but this methionine is again special there is a initiator tRNA, this methionine group is formulated. Does it make sense? These few things I want you to know. And then once the translation is assembled, transcription initiated, it goes to elongation. There are many elongation factors in like transcription which support the translation. We are not getting into detail, but what I want additional stuff is to show is that how exactly this peptide bond formation takes place. So we need an enzyme. Alright? So what is the chemical reaction? So this is your tRNA, alright? This is O. Can you see? Let me go inside. So whenever there are two tRNA, coming together, you have one tRNA correct, and this is connected with correct. This is a amino acid tRNA. So amine group. So this amine group of one tRNA will attack this carbonyl group, so that if I draw another, correct? I am not doing the whole thing. Correct? These are two tRNA. Amine group of one tRNA will attack this one, so that your peptide bond is formed. Does it make sense? This is a chemical reaction exactly takes place, and this is catalyzed by the enzyme called peptidyl transferase. Peptidyl transferase is the enzyme which catalyzes this peptide bond formation, and the peptidyl transferase activity is actually not a protein. It is present in the 23S ribosomal RNA, which is the bigger subunit of ribosome. Bigger subunit has 5S and 23S, correct? And peptidyl activity is actually part of this 23S ribosomal RNA, which is part of the large subunit of ribosome. This is the chemical reaction you want to know. Amine group of one amino acid tRNA reacts with correct this carbonyl group. So you form the peptide, bond, and this reaction is catalyzed by 23S ribosomal RNA 2451. This is the position of this adenine group, and this adenine group acts as a catalyst. Does it make sense? This particular adenine group in this ribosomal RNA at 2451 position helps So basically, the arrow is wrong. I think that's not correct. Correct? The arrow has to be from this to this hydrogen. Correct? Book also sometimes does mistake. So basically, it's a basic heterocyclic amine. It's heterocyclic base, takes the proton away. This becomes a nucleophile, attach the acetyl group, correct? Ester group in the tRNA, amino acid pair, and produce NCO group. So this time the peptidyl transferase, which catalyzes the peptide bond formation, is actually an RNA molecule. It is the 23S ribosomal RNA, which is part of the large subunit of the ribosome. And in case of E. coli, this position is fixed, that adenine group at the 2451 position acts as a general base. Does it make sense? We studied general acid base catalysis. It acts as a base to deprotonate so that the amine can act as a nucleophile. Is it clear? So once you form the peptide bond, ribosomes move one codon forward. Correct? New protein peptide is out. It goes forward until it reaches the stop codon. Does it make sense? There are the proteins which help this translation, elongation, and so on. So I think these are all about translation. I wanted to talk little bit about the tRNA structure, little bit about the ribosomal RNA structure, correct? And genetic code, correct? And how exactly codon anticodon pairing takes place, how tRNA is loaded with a specific amino acid, amino acid tRNA synthetase, and then how tRNA binds to the correct codons in all our ribosome cells with the peptidyl transfer activity to synthesize new proteins. Does it make sense? So overall, you want to have some idea that how exactly translation takes place. Any question anybody has?
Which side is which are those amino acid tRNA groups? Which one would be the P side and which one is the A side?
So which one will be the P side, which one will be the, so the new one will have, correct?
The one that's attacking is going to be on the A side?
The new one will have a preamine group.
That's just for the first amino acid.
Whenever a new one is coming, it is coming with a preamine group.
Oh, okay.
It could go in the other way as well, but I have to check. I think the amine group, the new one amine group will be connected with the ester group of the P side.
On the P side.
Correct? Your question is whether the amine group from the P side works with A side ester or the reverse, correct? That's what your question.
Yeah.
Yeah, I think the amine group of the, I'll check it if I'm wrong, but I think amine group of the A side. Yes, it's right. Read this section of the book, it should be clear, but if there is a question, you can talk with them. So there are a lot of ribosomes, a lot of proteins. Correct? Large, big RNA, large protein. We don't know the function of all the proteins, but they have definitely some function, initiation, elongation, and so on. I like this picture. This is electron micrograph. So whenever, what it means is that whenever a RNA is translated, right? So something starts, a ribosome starts at the beginning, it continues till the end. Does it make sense? Now, starting another translation, another round of translation does not need to wait till the end. Okay? As soon as the ribosome has moved little forward, it can initiate another round of translation even if the first one is not completed yet. Does it make sense? So that from the same mRNA, you can get multiple copies of protein in a short time. This is a fantastic electron micrograph. I think I was talking to US. So this is RNA, okay, and the ribosome particles is assembled. Multiple ribosome particles is assembled on the RNA strand, and as it proceeds further, you can see this bigger peptide protein. So those which have progressed little forward, they have bigger peptide as well. Does it make sense? With the beginning, they have small peptides. But at the same time, there are multiple ribosomes involved in the translation. Yes.
So the upper right would be the 5' end of the.
This should be the 5' end because you are
longer.
yeah, right?
Yeah.
So here you have bigger peptide. Fantastic picture. Electron micrographs. Sometimes electron micrographs are so beautiful I can watch them for a day. Right? It's so fascinating. Okay, so I think this is the last slide which I want to talk. There are many antibiotics which we use for killing the bacteria. Right? When you have infected with bacteria, we use antibiotics, and many of these antibiotics actually stops the translation. The protein synthesis blocker. Various antibiotics that act on protein synthesis inhibitor, pyromycin, and so on. So basically, they mimic some of the DNA structures and bind, so they block the translation. I don't expect you to know the details of the structure, but at least know that antibiotics, many antibiotics work on translation, some antibiotics work on transcription, right? Bacterial transcription is inhibited or translation is inhibited so that the bacteria cannot grow. Does it make sense? Chloramphenicol. Chloramphenicol is a very common antibiotic, correct? So it's a translation inhibitor. This slide is not. Erythromycin, chloramphenicol, pyromycin, streptomycin. So these are all translation inhibitors. Okay. So this slide is from the book, so know these 4 drugs: chloramphenicol, erythromycin, tetracycline, streptomycin, and pyromycin. I said 5, correct? So chloramphenicol, erythromycin, tetracycline, these are common antibiotics. If you go to doctor, something with the infection, they will give some of them. Sometimes they will give penicillin. Right? For some people, one drug do not work. Penicillin do not work for many people. So streptomycin is our puromycin. Okay, so these are the this is streptomycin. Chloramphenicol, erythromycin, streptomycin, puromycin. You cannot see them, correct? Let's enlarge this schedule. Now can you see a little better? Yes? Now if you look at the structure, correct, you see some of these groups. What are those groups? Sugar. What is the function of sugar? Anybody? If you remove this sugar, the antibiotic does not function. What is the function of the sugar? Normally, the sugar has the ability to form lot of hydrogen bonds. Correct? So, they are involved in the recognition. This time they have to bind the ribosomal RNA, non-covalent bonds, correct? Hydrogen bonds. So sometimes they are involved in recognition, sometimes they are involved in localization in the cell. So primarily I think sugar is involved in the recognition. So that's why if you remove the sugar from these, they will not function. These are all some of the cyclic peptides. These are cyclic peptides. Again, peptides also has a lot of hydrogen bonding pathways. Okay. See again here, the erythromycin has some sugar and some other stuff. Sugar in general, I think, is involved in the recognition compared with activity specifically. Any other question you have? Yes.
So you want us to know the structures of these? No.
Would you like to know for the exam?
No.
No, I don't expect you to know the structure. But I do want you to know that these drugs inhibits the translation. Does it make sense? So there will be a multiple chart that what is the mechanism of action of streptomycin? Correct? It inhibits transcription, it inhibits replication, translation, and so on. So if you are working with these antibiotics, at that time you need to know the stuff. Any other question?
On the N-formulated methionine, it's on the tRNA, right?
Initiator tRNA.
Okay, so then for the mRNA, the AUG is on the mRNA.
Yeah.
So how does that specific N-formulated methionine know to go to the first AUG on your mRNA?
This has to be recognition through the ribosome.
Okay.
Alright? Ribosome does all the play. So whenever you have RNA, it starts to scan where is the first one. Okay? Normally it starts to bind the first one and brings the first tRNA initiator tRNA to the first one. But sometimes in RNA you have multiple AUG and they are all in frame. Okay, if they are not in frame compared to the first, then they are not really AUG, correct? But there could be multiple AUG in frame and they are very close. And sometimes you do see that multiple different proteins. These are subtypes, isoforms. You can make the different isoforms starting at different start sites.
All this is gonna be on the file right now, missing there.
So I thought that whatever I said yesterday for the amino acid RNA synthesis will go. So this will be in the final. But whatever we did in the last class, let's put it some questions in this section.
So the exam, then Tuesday
Any
stops
other question you have?
from what we
Oh, we need to review.
yeah. This is the
So this chapter, do I need to review anymore? I said what you need to study. Correct? You want to do it again? Okay. So you go for the
So German,
genetic code, basics of genetic code. Know the first amino, first genetic code, and stop codon, correct? And initiator, start codon, stop codon, and the first codon discovered, correct? And then little bit about the tRNA basic structure, how big those are, the sequence CCA at the 3' overhand, the chemical reaction, how tRNA is charged with a specific amino acid, with amino acid tRNA synthesis. Basically, you need to know the reaction. I can ask you, draw the chemical reaction, correct? For the specific, for phenylalanine specific tRNA synthesis. Correct? You draw a tRNA structure, a cartoon, 3' end, you make sure you put CCA, draw the A, and do the acylation reaction. Does it make sense? So once you have that, then you go for translation mechanism, correct? Initiation, elongation, and termination. This we already said. And what is special about initiator tRNA? Then forming methionine tRNA is the initiator tRNA, correct? And know how exactly the peptidyl transferase activity works, little bit ribosome structure, which subunit or which ribosomal RNA has a peptidyl transferase activity, correct? You don't want this section, you said in the okay, up to tRNA synthesis, you keep it. Rest you forget. Now. Okay? Alright, then let's go for what did we do last one? Transcription. Okay? Transcription, you need to know the prokaryotic transcription in detail. Correct? Promoter architecture of prokaryotes, -10, -35 sites, -10 sequence, composition of the RNA polymerase, alpha to beta, beta prime, function of sigma factor. Correct? The translation, initiation, elongation, termination. Promoter structure, initiation, elongation, termination. Abortive transcription, initiation. Correct? Small transcription form until the RNA polymerase finds the stable transcription elongation complex. Correct? Mechanism of termination. There are two different mechanisms. Correct? One is row dependent, another is inverted repeat for you. Does it make sense? Then you have transcription regulation in eukaryotes. We went over lack of pheromone. Details of the lack of pheromone. Eukaryotic transcription, eukaryotic promoter architecture, transcription, initiation mechanism. What are the transcription factors involved in eukaryotic transcription? How the transcription initiation complex is assembled, correct? General transcription factor, RNA polymerase 2. Does it make sense? We did not go for termination there, elongation there, all this, but initiation mechanism we want to do that. Then function of chromatids. chromatids. So you have nucleosome, you have 4 different histones. What is the function of histone? Correct? And I think we discussed 2 or 3 histone modification. Histone acetylation. Correct? What is its impact on gene expression? Histone deacetylation. What is its impact on gene regulation? Correct? And some methylation. That's it. What else did we discuss here? Anything else? And then we have the replication. Correct? Again, replication. Let's go to the slide. Replication. Reaction mechanism. What is the chemical reaction takes place in replication? What is the chemical reaction takes place during the transcription? Correct? So replication is semi-conservative, bidirectional, concept of Okazaki fragment. Correct? And the functional differences between pole 1, pole 2, pole 3. What are the enzymatic activity they have? Mechanism of nucleotide incorporation, chemical reactions for nucleotide incorporation, chemical reactions for proofreading. How exactly Okazaki fragments are connected? Does it make sense? With DNA polymerase 1. And replication force. Draw a functional replication force, right? When you draw with a diagram, right, brief. Okay. Draw the diagram, put the right protein, label it, what date it does. Right. Don't write 2 pages because I don't look at 2 pages. Correct? So this is the nucleotide incorporation mechanism. Clinofragment, what is it? So-called clinofragment of DNA polymerase. This is application for know the cell cycle progression. What happens in this stage of cell cycle? Telomeric DNA replication. If you are confused the telomeric DNA replication, there is a YouTube video. Just search for telomeric DNA replication. You will get the details very easily. And tell you which one. Telomeric sequence. How are viral genome replicated? So reverse transcriptase and the viral drug, antiviral drug is used. I think recombination only focus on homologous recombination. Model, collect a model for homologous recombination and try to recognize few proteins which are involved in this homologous recombination, which are REC, A, B, C, D, RUF, REC, RUF, all these are involved in recombination. And then what is mutation? Do we have here? Yeah. So we did not go over others, but look at a little bit mutation, what happens to EV damage, what chemical reaction, alright? Not detailed chemistry, but you know what happens. And how exactly it may be repaired, then how some oxidizing agent, nitrous acid, how they induce mutation or what mutation. If you treat the cells with 5-bromouracil, what happens? correct? So you have 82, this is an 2-aminopyridine, it's a mutagen. What happens? Oxidation of adenine produce hydrogen. So these mutations you want to know the result. So I can ask, you take the cell to 5 or expose the cell with 5 amino acid of 2-aminopyridine. What will happen to the cell? Does it make sense? What specific mutation it does? Oxidation of adenine. What specific mutation it will do? I think that's it. Any question you have? So we'll have again the same, yes.
Can you explain abortive transcription, like what it is?
Abortive transcription, whenever the transcription is initiating, all the proteins are assembled, okay, it starts to transcribe, so it does not need a primer, correct? RNA polymer, so it starts to form the first phosphodiester bond, dinucleotide, then add 3, 4, 5, 6, and 7, and so on, correct? So eventually the RNA polymerase has to go into the elongation phase. But before it goes to elongation phase, it tries to make sure that it can start efficiently the transcription elongation. So it tries to form a stable transcription elongation complex before it can run. In that process, it initially tries to make that elongation complex. All do not get successful. So all initiation do not go to the end. If it does not go to elongation, correct? So short transcripts are aborted, released into the solution, okay? Until it finds a stable elongation complex for the completion of the run. So this release of the transcript finds a stable transcription elongation complex is called abortive transcription. Does it make sense? Any other question? This section is fairly straightforward. Please read and whatever we discussed, if you study this, should not be a problem. Okay? Any question? No? Okay. So all right. See you on
Did you read the article? And today, the group that I'm gonna be in, I'm just gonna tell you like, hey guys, I'm really sorry. I wish I could really be helpful.